problem that I have.
Okay, cool. And I just hit record, so the session will be recorded. And
Okay.
I will send you a link probably tomorrow morning as to how to see the recording of it. So
Okay.
I'll need an email address to send it to. And you want me to use the one that you're sending that thing from right now?
Actually, I was wondering if you could work on this first problem.
Yeah,
I'm having
no,
trouble with.
I just mean that as far as sending you your email address is this one here, nick.darrow at...
Oh, yeah.
Okay,
Yeah.
yeah,
That's my main email address.
yeah, okay, that's all I need to know. A place to send the thing tomorrow.
Mm-hmm.
All right, let me rotate this. All right.
So I worked on it a little bit in class for what I could like get done, but other than that, I'm having a lot of trouble with this.
All right, we're doing 15?
Yes.
Okay. Oops, hold on. So 15, let me write the whole thing out over here, and then I'll blow this up and we can talk about it. All right. First of all, when you see a problem like this, always, if you can, factor anything you can factor.
Mm-hmm.
You factor the numerator.
Okay. So the numerator can factor to x plus 2, x minus 2.
Okay. Now, typically, they want you to graph this, right?
Yeah.
What else do they want? Do they specifically ask for anything? Yeah, let's see.
They want the domain, the intercepts, the vertical asymptotes, the horizontal asymptotes, and the whole if there is one.
Okay, that's typical stuff. That's what they always want, are those things, okay? So, let's start with vertical asymptotes. Where do you traditionally find vertical asymptotes?
Huh? Sorry? I'm sorry.
Where do you traditionally find vertical asymptotes? What causes a vertical asymptote?
In the denominator, right?
Division by zero. Right. In other words, whatever makes the denominator zero would traditionally cause an asymptote. This is slightly different because one of these factors, in other words, normally I would say, well, I'm going to have vertical asymptotes at x equal 1 for that one and x equal 2 for that one. Okay? But this is different because one of these factors is cancelable with the numerator, that one right there. It changes my vertical asymptote. The only vertical asymptote I have left is x equal 1.
Okay.
Okay, so I'm going to start my graph there. Okay. Now, the fact that we canceled that doesn't totally change the domain. In other words, x still cannot be equal to 2. Even though our function now looks like this, and if I was looking at just this final function, I would not see that domain restriction. The only domain restriction on this is x can't be 1. But the domain restriction still follows it as a whole. X cannot be equal to 2. So whatever my final graph looks like, I'm going to put a hole at x equals 2 instead of a vertical asymptote. And that's the way all of these work. Okay? Now, let's talk about horizontal asymptote. where is my horizontal asymptote? So this one's a hole instead of a vertical asymptote. Let me uncross that out. We have a hole at x equal 2, which means x cannot be equal to 2 or 1. But horizontal asymptote, how do you figure horizontal asymptotes?
I'm a little unsure. I wasn't here that day.
Okay, let's start from different. There's 3 scenarios. Okay, one scenario would be like this: x minus 1 over x squared plus 7. Okay?
Okay.
In this scenario, the highest degree in the denominator is bigger than the highest degree in the numerator, right?
Yes.
Long as that is the case, you have a horizontal asymptote at y equals 0. The x-axis is your horizontal asymptote. And it doesn't matter if this was x to the third, as long as the highest degree in the denominator is bigger than the highest degree in the numerator, your horizontal asymptote is y equals 0. The other situation, there are 3 situations. The other situation is when the highest is the same. Like, let's say we have 2x squared minus 1 over 3x squared plus 7. Well, we have an x squared highest there and x squared highest there. The horizontal asymptote is the ratio of their coefficients. In other words, y equal 2/3.
Okay.
That's situation number
the ratio
2. Ratio of the coefficients. And it wouldn't matter if that was x to the 5th and this was x to the 5th. If they are the same, and it's the highest one, then the horizontal asymptote is the ratio of the coefficients. There's one,
and it's the leading coefficient?
Yes, the coefficient of the highest degree of x.
Okay.
We really don't care. When you're talking about asymptotes, I don't care about anything else. That is immaterial if I add an x cubed over there. The only thing I care about is the highest degree of x in the numerator and the denominator. And in this case, it's x to the 5th. So it's always the ratio of the coefficients of that highest degree variable.
Okay.
I don't know what's going on here. Wow, that's really weird, huh? Computer just did something weird. There's 1/3 example. And that is where the degree in the numerator is exactly 1 higher than the degree in the denominator.
Okay.
Okay, like that. And the way you handle this always results in an oblique asymptote. Slant asymptote, you familiar with that?
Oh, yeah. That's the next problem, actually.
Right, and when I divide this by this, I'm going to get a linear term, something like x plus 5 with some remainder. Well, I don't care what the remainder is. The equation of the linear term is the equation of the slant asymptote.
Okay.
Okay, so that's the only kind of horizontal or slant asymptotes that you're going to have. It all comes down to the highest degree polynomial, or the highest degree in the numerator and the denominator, and what their coefficients are. So in this case, what do we have in the numerator for the highest degree, and what do we have in the denominator for the highest degree?
In the numerator, we have a 1. In the denominator, we have a 1.
In the numerator, we have a 1, but in the denominator, we have that.
A -1.
So that means the horizontal asymptote is y equals -1.
-1.
Okay, so That's all you have to do. In other words, we did have to put these back together again, but only to the point of knowing what the x squared coefficient's going to be. And obviously, that's going to come from minus x times x, which is this minus x
Okay.
down here.
Okay.
So now I can draw the horizontal asymptote at y equal -1. Okay. Now, all of these, well, I don't know about all of them, but this quotient is hyperbolic in nature. Okay. It is going to look like either this or it's in these quadrants here.
Okay.
Okay? Almost all of them. Sometimes you'll have not 4 quadrants, but 6 quadrants, and you'll have 2 vertical asymptotes. And then it does something a little bit different. But whenever you end up with 4 quadrants, like we have here, you know, especially looking at this right here, that it's one of these 2 graphs I've drawn. The one in black or the one in red. Now, there's a couple other things it asks for. One was, let me move this over so I can see it. The intercepts. It wants
yeah, that's a big one.
It wants that we've got the vertical asymptotes, although that's not right.
Yeah. Now I know it's not.
Vertical asymptote at 1, but there's a hole at 2.
Would the whole as a point written out be 0, 2?
It would actually be 2, comma, whatever you get when you plug in 2 into this.
Okay.
In other words, if I plug in 2, I get, that's a 2 there, right? I get 4 minus 1. So minus 4.
So it'd be -4.
It'd be 2, -4 is where the hole is.
Okay.
Okay. There is a horizontal asymptote at y equal -1.
Yeah.
Now let's talk about the intercepts. Okay. Intercepts. What is y when we're talking about the x-intercept?
When we're talking about the x-intercept, y is any
0. Always 0.
0.
In other words, whenever we're on the x-axis, if I look at this point right here, y is 0, correct?
Yeah.
So whenever I'm looking at x-intercepts, I know y has to be 0. Well, how about y-intercepts? What is x?
0.
Okay. Really good thing to know is that right there. Is that when you're talking x-intercepts, y is 0. When you're talking y-intercepts, x is 0. So let's start with our final equation, y equals x plus 2 over 1 minus x. That's all we really need to determine intercepts. Well, the easiest one to determine is the y-intercept. Because all I have to do is substitute 0 for x. Well, what do you get?
Okay. You get 2.
That's this one right here. That's where 2 is. In other words, it's not the black one. Notice that the black one, this one would be minus 2. So I immediately know that it's not the black curve, it's the red curve. Let's erase the black curve and go with the red curve. Now let's make sure the rest of the points make sense. And you can tell from the red curve that we only have one y-intercept. And it's at 2. Now, for the x-intercept, we're going to set y equal to 0 and see if we can solve this equation. There isn't always x-intercepts in these, but there usually is. In other words, the only time and there's not going to be an x-intercept is if your asymptotes are the axes. In other words, the y-axis and the x-axis. If those are your asymptotes,
Okay.
you're not going to have an x-intercept. It's not going to go through the x-axis. But in this case, since we're shifted 2 units to the right and 1 unit down, that's basically what this grid is telling you, well, it looks like we do have an x-intercept right there. So we should be able to find a solution to this equation. Well, when I have a rational quotient equal to 0, what has to be true? How would you solve that?
I would multiply the numerator by the denominator.
Okay, well, you'd multiply both sides by 1 minus x, correct?
Yeah.
Okay. Well, what's that going to give you is 0 equals x plus 2.
Okay.
Okay? So the thing to really take away from this is that if you have a rational quotient equal to 0, it can only be equal to 0 if its numerator is equal to 0, by definition.
Okay.
So we don't have to actually do that step where we multiply both sides by 1 minus x. We can just know that for this thing to be 0, the numerator has to be 0. Well, in this case, the numerator can be 0. It's when x is minus 2, right? So here is the x-intercept, minus 2 comma 0. There's the y-intercept, which is 0 comma 2. And that's the only 2 intercepts we have.
Okay.
Now, the numerator isn't, let's say I had something like this. See, what the change I made it was x squared?
Yeah.
Now notice that there is no value of x that makes the numerator 0. If I were to try to graph this function, I would not have an x-intercept. And I can tell by the fact that this number is always greater than 0. X squared plus 2 has to be greater than 2, always, because x squared is always a positive number. So you won't always be able to turn the numerator into 0. In this case, you can, though. And
okay.
I think there's only one last thing to do, and that is to put the hole in there at x equal 2. And what that looks, not x equal, oh yeah, this was 1 here, yeah, excuse me. X equal 2 is right there, so the hole goes right there, and the coordinates on that hole are 2, negative 4.
4.
Okay?
Okay,
now,
cool.
If you were to graph this original function in your calculator, not going to show you the hole.
No. Okay.
You know why? Because that hole is infinitesimally small. It is only when x is equal to exactly 2. Well, 2 is just 1 point out of an infinite number of points between 1 and 3, right? So it's really tiny. What's the width of that point? Almost 0. So that hole that your calculator might see, but when it goes to graph it, you don't see it because it's much smaller than the resolution of your graphing calculator. So don't rely on your graphing calculators to show you the holes. Do you have an Inspire or do you have a TI-84?
I have a TI-84 Plus.
Know that the TI-84 does not show the holes. I'm not positive I'm not positive about the Inspire. The Inspire may have figured out a way to recognize that there's a hole there and put it there, but the TI-84 will not show you.
Yeah, and I think that's okay because on the test she's not allowing calculators.
Okay, cool. And I think we got everything. We got the domain. This is the correct domain, actually. In other words, the domain...
I think I know how to...
Yeah, the domain is going to be all reals except the vertical asymptotes and the holes. Those are never going to be in your domain. Okay. All right.
Okay. Cool.
Let's see. We've got a half an hour. Should we go to 16?
No, I'd actually like to go with this 17.
Okay.
So I can actually read it to you right now.
Okay.
That's all. You can kind of see the top of it, but I can read it off to you.
No. So he has 2,400 feet of fencing.
Yep, and he wants to fence off a rectangular field that borders a straight river.
Okay.
And he wants to know what the dimensions of the field are that has the largest area.
So is this the correct picture?
Yeah.
Okay. And we have 2,400 feet of fencing material. Well, the very first thing we need to do on this problem is, like all word problems, there's a very, very simple first step that will make all word problems so much easier, and it's always define your variables. So in this, I'm going to let x be the width, y be the vertical height, like that. I could do it opposite. I could let x be the vertical and y be the horizontal, but I stick with the convention, which is x tends to be the horizontal measurement, y tends to be the vertical. Now, the question says, figure out the dimensions of the corral so that you have the maximum area, right?
Yes.
Okay. So we need an area function. What's the area function?
Area function would be x times y.
Okay. Well, we can't do much with that, but we have a secondary function. What's our secondary function? We know that something equals 2,400. If we use all the...
wouldn't 2y plus x equal 2,400?
That's our secondary.
Okay.
Okay. And what that's going to do is allow us to determine either x or y in terms of the other variable. In other words, if I solve this top equation for x, let's do that. Well, then it's equal to 2,400 minus 2y. Okay. Now, since I've defined x in terms of y, I can go down here and plug it into the area function. Instead of x, I'm going to write 2,400 minus 2y and multiply that by y. Now, notice that when I multiply that, I end up with a quadratic in y.
Yeah.
And quadratics either look like this or they look like this. Okay? Well, this quadratic is going to have a minus 2y squared. So it's going to point downward, and that point right there is where we will have a maximum area. In other words, if I graph this quadratic, let's say I graphs like that, this is the area and this is y. Now, sorry to confuse you by making the horizontal axis y, but it's whatever the independent variable is your horizontal axis. And in this equation down here, it's y, which means your vertical is a. That's a. Now, I could have solved this original equation for y instead of x, and then I would have substituted for y, and I would have had a final equation in x. Does not matter whether we solve for x or y. Once we solve for one, we're going to know what the other one is, because that's y over there, okay? So the fact that we're solving for y doesn't hurt us at all. Okay? Now, the question is, how do we figure out So my area function, if I multiply these two things together, I get, I'm going to put the big one first, minus 2y squared plus 2400y. Okay.
Mm-hmm.
Well, if I want to, that's a parabola, and I want to know where the vertex is.
Oh, isn't that negative b over 2a?
Beautiful. Vertex is its x-coordinate. What is normally the x-coordinate? I'm really going to confuse you now. In other words, the horizontal number, this number right here, is minus b over 2a. So what is that in this case? What's minus b?
So that'd be negative 2,400 over negative 4. And that comes out to be 600.
That's y.
Okay, cool.
Okay, the fact that it's y, and I've called this the vertex of x, you understand what's going on there?
Yes.
In other words, typically you have an xy grid when you're looking at parabolas. You have a grid where the horizontal axis is x and the vertical axis is y. Okay, so when I talk about the vertex, the x-coordinate, I'm talking about a picture like this, and I'm looking for that point right there. Okay.
Okay.
Well, this problem is a little different. It just turned out that randomly solving it, it's the vertex of the horizontal coordinate. And in this case, y is the horizontal variable. So it's really, this is the vertex of y. So y is 600 feet. Now if we go back and we look at our picture, let's see if that makes sense. If that's 600, and that's 600, then this has to be 1,200 if they total 2,400, right?
Yeah.
That is the proper dimensions that will always maximize that three-sided rectangle. It doesn't matter whether you're up against a river or a building. As long as you only have three sides, then it's always the length dimension is going to be twice the height.
Okay.
Yeah. In the same way that if the problem was build a corral out in the middle next to your barn, and you have a certain amount of fencing material, it always comes up to be a square. Okay? In other words, if you have to build a four-sided shape, a square always gives you the maximum area. If you're not restricted by anything, a circle is what you would build. In other words, if
that gives you the maximum.
Yeah, if I give you 1,000 feet of wood and I say, go build me the maximum sized area of a corral, I'm going to build it in the shape of a circle. That gives you the maximum bang for your buck. And that's why corrals were built circular. They got the most area out of a given amount of wood.
Okay.
Okay.
Okay, cool.
All right. Let's see. Was there did you send me a second picture?
No, I have another word problem. Or like problem I can relate to you verbally.
Okay, yeah, you can probably read it. Go ahead.
So the problem is 4 minus 3i is a 0 of the function x to the fourth minus 9x cubed plus 21x squared plus 71x minus 300. And it says, minus 300, yeah. And then it says find the remaining zeros, and I must use 4 minus 3i for the first step.
Okay. What's another zero? If 4 minus 3 is 1 0, what's another one?
4 plus 3i.
Ah, that's the key. They always come in pairs, imaginary solutions. Okay?
Yeah.
Now, if I take this polynomial and I divide it by 4 minus 3i, I'm going to get one factor and I'm going to get a cubic left over, right?
Mm-hmm.
Okay. Now if I take that cubic and divide it by the other known zero, 4 plus 3i, I'm going to get a quadratic left over.
Okay.
Once you can get it down to these two solutions plus a quadratic, well, now you can always factor the quadratic. Worst case scenario
Yeah.
is you have to use the quadratic formula. But that's the key on all of these, is getting it down to a quadratic. Because we have a quadratic formula. We don't have a cubic formula. There's no such thing.
Yeah.
Or a quartic formula. If they just gave you this
That'd be
polynomial and they said find the zeros without a calculator, I might still be working on the problem next Tuesday. It's that hard. It really is. So,
oh, wow.
yeah, who knew? Yeah, no, but it's true. Because we don't have formulas for the bigger polynomials. We can handle quadratics, but anything bigger requires some very sophisticated solutions, which we won't get into here because we don't need to. The fact that they gave you one of the zeros and it was complex means you know another one. Now that you know that there's going to be 4 zeros to this thing, you generally have the same number of zeros as you have degree of polynomial. Okay, so this gives you 2 of them, and we're going to be left with a quadratic, which will give us the other 2. Now, let's talk about how we get the leftover quadratic. You familiar with synthetic division?
Yes.
Okay. Let's synthetically divide these by these 2 answers. Let me think for a second if there's maybe a better way to do this. There might be. There might be. If we multiply these 2 together, it'll give us a quadratic.
Yeah.
If we take that quadratic and divide it into this quartic, I'm going to get the remaining.
You get another quadratic?
Yeah, I'll get the other quadratic. And the other one is the one we want. And that's probably easier. You could also do synthetic division. In other words, I could do synthetic division of that one and take whatever I get down below and then synthetically divide it by that one, and I'm going to end up with that quadratic that I'm looking for. But doing synthetic division with complex numbers is not the easiest thing. I can certainly go through it with you if you want to go through it, but I suspect the easiest thing to do here is going to be to multiply these together and come up with a quadratic.
Yes,
boy,
I'd like to do that.
Yeah, not that easy actually.
Maybe.
Now that I think about it, because what we really have is x minus that and x minus that. In other words, these are the factors. And so if I want to come up with a quadratic, I have to multiply this trinomial by this trinomial. And I will come up with a quadratic. Okay.
It's kind of hard.
It is kind of hard. And in the same way that if they told you one of the zeros was 5, you wouldn't divide by 5, you'd divide by x minus 5, right?
Okay, yeah.
In other words, there's a difference between the zeros and the linear factor. This is the linear factor. The 0 would be at 5. So if these are my 2 zeros, these 2 complex numbers, then the factor is actually x minus those. And now we have a trinomial and a trinomial. That's getting more complicated. We can certainly multiply those 2 together and come up with a quadratic, and you will see that the imaginary part disappears. When I multiply this by that, I'm left with just real coefficients.
Okay.
So I'm not sure that that is the easiest way. The fact that we have to turn it into a trinomial. Let's have a look at synthetic division here.
Okay.
Okay? So let's lay out, and I'll show you what happens with synthetic division. And you have to allow for every power of x. Now this happened to have a term for every power of x, but say this 71x wasn't there, you'd need
Wouldn't you put a 0 there?
a 0. It's like a ghost, a placement marker.
Okay.
Okay? What I'm going to put in here is 4 minus 3i. The 0. In other words, what always goes in the box is the 0, not the factor.
Okay, yeah.
I'm kind of thinking this might be the easiest way. I'll show you what happens. Okay, we bring down the 1. Are you good with synthetic division?
Yeah, I understand. Yeah.
Okay, let me go ahead and complete it then, just to speed things up. Now I'm always adding. So when I add these two numbers, I get minus 5 minus 3i. You understand that?
Yes.
In other words, I'm doing minus 9 plus this number here. And that gives minus 5
yeah.
minus 3i. Now I multiply this by this. Well, let's do that. Let's see, what do we get? Let me do it over here and then I'll simplify it. We get minus 20 minus 12i plus 15i plus 9i squared. Did I do that right? In other words, I'm multiplying this times that in order to write something there. Okay, and I just did it by foiling it. Minus 12i is correct, plus 15i is correct, plus 9i squared is correct. Okay, now let's simplify this over here. You can always break down your I squareds. I squared's equal to what?
-1.
Okay, so that turns into a minus 9. So the number part is minus 29. Combine my i's, and I have that. That's what goes right here. Minus 29 plus 3i. Okay?
21, 29. You're left with -8 plus 3i.
Okay.
And so now I multiply -8 plus 3i times
now
4.
we can do the same thing again. So what does that give us? Minus, boy, I'm not sure this is easier or harder. Let's see. We got plus 12i plus 24i minus 9i squared. So let's see, that's a plus 9, so that gives us negative 23 plus 36i.
Yeah.
Okay? Now, what's going to happen is when I get all done, then I'm going to divide this answer here on the bottom by the second 0.
Okay.
Okay? And that's going to leave me the quadratic, and all the imaginaries will disappear. Let's kind of finish this. This is such a long problem that I hate to use our entire session with it, but let's...
Oh, that's okay. Because that was kind of like, that was pretty much the big problem.
Okay. Well, let's finish it then. Okay, and then let's see. This one becomes 4 times 48, 192 plus 144i minus 1, well, that's nice of them, minus 144i minus 108I squared. Okay, notice.
And that gives you plus 108.
Added to that gives you
That leaves
300.
300.
Exactly.
Okay.
That gives you that zero remainder, which you're always going to get a zero remainder if that's a true zero. If it's not a true zero and you don't get a zero remainder, then that's not a zero. Okay, that's the zero remainder theorem. Says that if you have a polynomial and you're telling me this is a zero, then when I divide this into that polynomial, I will get a zero remainder by definition. Okay? Now we're going to do it one more time.
Bring down that.
And this time we're going to put this zero in there. And we're going to divide it into this right here. Okay? So let's try it. Shall we complete this thing so we know what the answer is?
Yeah, I'm doing that right now.
Okay, well, I can pretty quick also.
12. He'll probably do it.
1. And then that's minus 4 minus, ooh, look what's happening here. Very nice things.
I like how the eyes are keep going away.
Yeah, I didn't realize that that happens like that. Yeah, this wasn't that hard to do, was it? Minus 36I. And that gives you your other zero remainder. And now we have our quadratic. So here's our remaining quadratic. X squared minus x minus 12. Okay, how does that factor?
X can't be 6.
Minus 4. Remind me to go over some factors. Let's go over some factors sometime. There's just nothing you need to be better at than factoring. Okay? It's never going to go away. You're always going to need to be able to factor. So I like to tell people you just can't get enough practice at factoring. So here's all of our factors. X minus 4 minus 3i and x minus 4 plus 3i. Those are the two zeros that they essentially gave you. And then these are the factors of the quadratic. So there's a 0, there's a 0, 4 is a 0, and minus 3 is a 0.
Okay, cool.
That's the way you do it. And I'm not sure whether that way is longer or easier than had I multiplied that trinomial by that trinomial, then I would have had two quadratics.
Yeah, that's okay though, because I understood that way a little bit better, I think.
Okay, good. Yeah, because then we'd still be faced with dividing this quartic by this quadratic that we would have gotten. And that kind of requires long division, I think. I'm not sure I
can
do that synthetically, but you can do it with long division. You'd still come up with this other quadratic. In other words, if I multiplied that x minus that times x minus that, I'd come up with a quadratic that when I divided it into this quartic, I would have x squared minus x minus 12 as the
cool. Okay, I have
It's not as hard synthetically dividing by complex numbers as it looks like it would be, although it certainly isn't easy, especially the first step. Notice the second step is always going to be considerably easier.
The second step was a lot easier.
Yeah, every step of the second one, the eyes disappeared every step of the way, and I'm pretty sure that happens always, almost by definition. Okay, so the toughest part is really that first part. That's where you have to do all the foiling. And boy, you just want to make sure you don't make a mistake. And what
Yeah.
is going to tell you whether you make there's an awful lot of multiplication and addition going on here, so it's really easy to make a mistake, but you would know it because you wouldn't get 0. If you get anything
Okay.
other than 0, you've made a math error. Because they're not going to give you the wrong
Okay.
zeros. If they tell you that 4 minus 3i is a 0, then it is. And when you divide that into the polynomial, you better get a 0 remainder. If you're not getting that, go back and redo your math until you do get a 0. That's about all I can say.
Yeah.
I'm not sure there's any other way to do it. But you can see that there's a lot of room for error there if we happen to so all you got to do is make one mistake, and you're not going to get that 0 at the end.
Cool. Okay. Can we go, just to refresh my memory a little bit, can we go back over the slant asymptote real quick?
Yeah.
Before we leave, just
Sure.
in the last 4 minutes?
Sure.
Because I'm a little unsure about that one. Okay.
Okay. Here's our rational quotient, okay? And I know I'm going to have a slant asymptote because the highest degree in the numerator is this one. Highest degree in the denominator is this one, exactly one less. Still there, Nicholas?
Okay, and then isn't your slant asymptote 3 over 2?
No. No.
Oh, nuts.
You have to do the division in this scenario.
Oh, yeah.
If it's the reverse, if it's squared in the numerator, cubed in the denominator, then it's a horizontal asymptote at y equals 0. If they're the same exponent, then it's a horizontal asymptote that is the ratio of those coefficients. In this case, it would be 1 if this was just x squared. But if the numerator is exactly 1 greater, then you have to do the long division. And I'll show you here. Let's just go through it real quick. Don't need any dummy variables. The slant asymptote is the equation of the linear factor that comes out of this, and you throw away everything else. Do you know how to do this long division?
Yeah. I think I understand where you're going now from here.
I'll do it real quick.
Okay.
And then that's going to be x cubed plus x squared plus x. Subtract, and I get minus 2x squared plus 2x, bring down the 5, repeat, x squared goes into there, minus 2, that's all I need.
Okay.
I don't care what
so then my slant...
In other words, if I now multiply this minus 2 back here and I get some remainder, so that let's say I have a remainder of 5 that's going to be divided by this divisor. Well, the equation of the slant asymptote is that, regardless of the remainder.
Oh, so I don't have to worry about the remainder.
No. In fact, that's why I said the moment you get that, you're done. You don't need to finish out the problem. As soon as you have a linear factor, that's a linear factor because the power of x is just to the 1, then how would I graph that? Well, y equal x minus 2 goes through minus 2. Has a slope of 1. There is the equation of that. Okay. It might also have a vertical asymptote somewhere. Maybe there's a vertical asymptote like that. And now it's still going to be hyperbolic in nature, so it's still going to look something like this.
Okay.
Or the red. In other words, I might be in the wrong quadrants. It might look like this, but it's going to be hyperbolic, and you just have to figure out which one it is.
Okay.
Okay, once you have a slant asymptote. And by the way, it's impossible with algebra to figure out those 2 points right there. The best you can do is put it in your calculator, put it on the trace, and find maximums. and minimums.
Okay.
And then it'll tell you what that point is. But if I were to ask you what the range of this function is, you're going to have to use a calculator to find it, because there's no way to algebraically figure out what that point is on the y-axis.
Okay.
Okay? So that's
cool.
Horizontal, or not horizontal, oblique. Oblique and slant mean the same thing if you hear the either term. Okay. Let's talk about the schedule here, because I'm a little not sure exactly what you want for the rest of the week. Let's see. Do you still want the Thursday evening at your house?
Yes.
Okay. How about the Friday afternoon at your house?
Yes, this week.
Okay.
And then I think next week I have like we didn't think about the tournament schedule and such. Fridays are going to be a little tough, so maybe like Thursday or Friday we can discuss better scheduling.
Well, here's what my next week looks like already. So if
cool.
you might need something on Monday, now's the time to grab it, because it may not be open by next week. I work this thing on a first come, first served basis, and unless somebody locks up, like you've locked up the Friday session, okay, nobody can go in there and take that from you. But if somebody comes in here and reserves something between 6 and 8 on Monday, and then you decide you want an appointment on Monday, there might not be anything available. So just think about that when you're trying to schedule these.
Okay. Do we want to do something next Monday?
The 20, what day is that? The 24th?
Yeah.
Yeah. Do you want to do?
If you want,
yeah, because I did sign.
I can put it in.
I did sign up.
Go ahead, Nicole. Sorry.
I'm sorry. I don't want to talk about you. I did sign up, Nicholas, for the 20th for 6:30. And then, did you talk about the Fridays? Okay.
Yeah.
So, do you want to cancel this, or you want to keep it, Nicholas? The 21st.
I think we can cancel it, because I don't think it'll be any. I don't have any new material from Thursday to Friday.
Okay, but I thought on Fridays you get what you do for the weekend.
No.
Okay, it's up to you.
Yeah. No.
So, David, is that okay if we cancel the 21st tutorings, those Fridays?
Sure. Do you want to cancel the Thursday?
We forgot.
You want to cancel the Thursday and
No, not the Thursday. We want to keep the Thursday,
okay,
but cancel the Friday, the 21st.
I just did. Okay, and then next week, do you want to add a Monday?
Yeah, the Monday the 24th. Do you want to do the online? Did that work out well tonight?
Yeah, I actually did.
Okay, and then now, and 8 o'clock's a good time.
So, he is. I think it's 8 o'clock.
Notice that somebody has taken that 8 o'clock session?
Yeah.
Can you do earlier?
Okay.
We could do 6, 7, 6:30.
Okay, you're just going to have to miss Evolve.
Yeah, that's fine.
That's fine. Yeah, so what time does he have on Monday?
I've
like
got
6:30?
Between 6 and 8. So anything works.
Between 6 and 8.
You want 6:30?
Yeah.
Yeah, for an hour?
Yeah.
Yeah, for an hour. So give me the marker, Nicholas, so I can mark that in.
Okay.
Okay, and then I had one on the 27th again. I tried to grab a lot of Thursdays at 4 o'clock.
Uh-huh.
The 27th I grabbed. What time was this one? 6:30? 6:30.
Let's see. Next Thursday you grab the 4 o'clock one.
Yeah, which is fine. That's great.
And then you still have the Friday in-person one. And you know what? You can always cancel that. I'm never busy on Friday, so it's not like that's taking up a spot from anybody. So if you
how about if we do this?
Last month,
because he has. Sorry.
Okay.
How about if we cancel all the Fridays? Only because we didn't take a look at his tournament schedule.
Okay. Let's do that.
So that.
I can do that.
And then if we need them, we'll go back in and grab them.
That works perfect, because there will always be a spot there on Friday.
Okay. Okay.
See, I don't have a lot.
So yeah. So.
Okay. So
and then I grabbed.
So we're set for Thursday, Monday, and Thursday for the next 3 sessions.
Yeah, and then
And this
that's for October, correct?
Thursday is going to be at your house, right?
Yes, just one more in person. If this one went really well, then I think we can go to the online one.
Yeah.
Yeah, after one more in person.
That's fine.
Yeah, so let's do that.
Okay.
And then, so I've got the 17th, 20th, 24th, 27th, and then in November, I grabbed November 3rd, another 4 o'clock on the Thursday, and I'll grab another. You want to do Monday the 31st? That's Halloween.
No. No, sorry.
Yeah.
You don't trick or treat anymore, sweetheart.
Well, they do in my neighborhood, so I may have to block off for the trick-or-treaters. I don't know.
Okay. What about Tuesday the 1st?
You can see right here his schedule.
Oh, that's tiny print, honey. I wear glasses.
Oh, he has a lot of people on Tuesday. Maybe we don't do a Monday that week. Because
Okay, so let's leave that week just for the 3rd of November at 4 o'clock.
You find you need an appointment and there's nothing there, call me, and sometimes something will open up, or I'll have blocked off a half hour for a break or something. I could do a half-hour session.
Okay.
So, yeah, don't. The schedule is not written in stone, is what I'm trying to say.
Okay. Yeah, no, thank you. I appreciate that. Yeah, I'm just trying to make it so that Nicholas has 2 contact points with you a week.
Okay, good.
So that's why I wanted to try the online thing, and it worked out great tonight. He's happy with it. So
yeah, and I will send him a link tomorrow morning that will let him watch this recording if he wants.
Oh, good.
Okay.
Good. So yeah, he can review it tomorrow night before his test on Wednesday.
Sounds good.
That'll be helpful. Okay. So did you get answered what you needed tonight?
Yeah, I actually did. A ton. Thank you very much.
Yeah, you're welcome.
Great.
Okay.
Thank you. We're so happy this is working out great.
Yeah, well, good. I look forward to seeing you guys on Thursday.
Sounds good. Okay. We'll see you then. Take care.
Thank you, Mr. Khan.
Bye-bye.
Bye.
Bye.
I don't know how long.